So first of all, congratulations to you and Adesso for your birthday, your 20th birthday. It's a great pleasure to be here and to talk about blockchains as which I personally and I'm sure many of you find as a very fascinating and exciting topic that has both lots of interesting components from the viewpoint of software engineering or computer science in general, but at the same time has a potential for significant impact across different industry sectors. I'd like to start though with a long-standing problem known in software engineering, which is really the problem of platform application co-design, or if you want, the interrelationship between a platform on the one hand and on the other hand an application architecture. So I'm using the word platform here in a very broad sense, so basically referring to any type of middleware or data management system that is application independent. So it's software which is typically on top of the operating systems, on top of the raw machines, but below the application layer. And we've seen many of such platforms over the past decades, starting in the 90s with Corba, moving on to Java EE, the Web Services Protocol stack, and the numerous different systems we have out there. And more of such platforms are being created due to changing application requirements. So new application requirements in the context of the web, in the context of IoT, they drive the creation of new platforms. Once the platforms exist, they're application independent at first, but then they can be used to build applications, and then they impose responsibilities on the application. So if you consider NoSQL stores, for example, they have been created, the variety of NoSQL stores that we have today. In fact, there's not one NoSQL store. There's a site, I believe, online that counts existing NoSQL store projects, and I think the count is above 250 now. So we have over 250 different NoSQL store implementations, and these systems, they exist for reasons such as increased or changing workloads, data volumes, web-specific requirements, where the traditional classical model of the relational database management system was just not appropriate or not good enough. Once these systems then exist, however, and I'm sure all of you have experience in working with NoSQL stores, you look at these properties of these systems and you find out they have an impact on the application architecture. For example, the NoSQL stores basically part from the strict consistency model that we know from RDBMS and only implement eventual consistency. So should there be any conflict in copies, the reconciliation purposes is being shifted towards the application, and inside your application you have to take care of that. So eventual consistency changes responsibilities on the application, same for limited querying capabilities and so forth. This is the price you pay. If you have a NoSQL store or any system that caters for high availability and scalability, there will be other things that are being compromised instead of it. So the question is, what about blockchains now? Can I ask who has actually experience with blockchain in this room? Okay, that's just a couple of hands. I'd like to give you today my perspective on what blockchains are and why I believe that they are so promising and why they're an exciting area both for us in research to look at as well as in industry to build really interesting applications that can make a fundamental change. So you've seen quotes like this. I'm sure you can basically look into the web, and every day you'll find news about blockchains. And there's probably a number of headlines where one more exaggerating or more intense than the other, talking about fundamental disruption or transformation of entire businesses and organizations, at the same time claiming, however, that this is not just a theory or belief, but it's actually, the potential is very real, okay? If you look at the blockchain project ecosystem and the number of companies and solutions addressing and dealing with blockchain, of course, the finance sector and the finance industry were first to start with a number of blockchain projects, but now we have the entire range across all different sectors in all different domains, whether it's the large global corporations or the numerous startups that exist that are dealing with this. And blockchains in the first generation were probably seen as the technology behind Bitcoin. So in the first generation, everybody was looking at blockchains from the perspective of cryptocurrencies, digital currencies. But at least with the second generation of blockchains, we're talking about blockchains as we know them since 2 or 3 years, we are no longer bound to financial and crypto applications, but we have an entire range, and the limits seem basically non-existing. Also, if we look at the startups that have been created and are being created almost on a daily basis, and including the investment volume that went into funding of these startups, over 1 billion was invested in blockchain-based startups just over the last 2 years. We're talking 2015 and 2016. And with a continuation in 2017 as well. This is really significant. Okay? So then, what is a blockchain? And I think we need to take at least these 3 perspectives. I typically like to describe a business view, then a technology view, and an architecture view. And I'm separating these 3 views, but we should all have each other's view in mind and keep them in mind, because only in combination they work. Okay? So for a business perspective, one definition of what a blockchain is that a blockchain is really a decentralized ledger, a golden, persistent, immutable record, a bookkeeping record that would enable trustless interactions and business disintermediation, and thereby lowers transaction costs, significantly can lower transaction costs. So basically the idea is to cut out the middleman. In the first generation with cryptocurrencies, the idea was basically take out the bank. If Alice wants to send Bob money, why would we need a bank? We remove the bank and have Alice send the money directly to Bob, so to say, in the digital world, just as we do it with cash in the real world. And this applies to nearly anything. The base premise is, why would we need an intermediary, a middleman, to trust? Remove that trust, and the only belief is trust yourself, and then trust in a network of peers that live according to the same principles, trusting yourself. Okay? So by removing out that middleman, this doesn't apply to banks, it applies to insurances, it applies to nearly any established industries. And this is why this is so powerful, and why basically all strategists in corporations across the world are looking into blockchains. From the technology view, I like to describe blockchains typically as a synthesis of a set of concepts. Each of these concepts individually is quite well known in computer science, partially in economics, and it's really the synthesis that breaks and brings a very powerful model. So one component is we're dealing with a peer-to-peer network. That's the starting element, right? Secondly, we're always talking about transactions. The key is we're not just storing data and talking about data in a general sense. We're talking about transactions. So anything where value is being exchanged, where something is transacted among different parties. In addition to the transactional data that is being stored on that peer-to-peer network, we also have, with the second generation of blockchains, digital contracts. And digital contracts are really executable programs. So we have behavior on the blockchain as well. It's not just a distributed data store, but it's a data store that also has executable logic that is being executed by each of the peers. Then these transactions are being secured. We put in a bit of asymmetric cryptography. We are already said, are only recording things that are agreed upon in the network, so we're requiring consensus protocols. And we also implement some incentive mechanisms that would actually incentivize different peers, for example, to validate transactions, to mine transactions, and then to propose them towards the block. Because transactions at the end of the day still cost money, not only for the transaction itself, but also for storing and managing these transactions. So easily said, possibly, but not so easy to digest, right? So this statement, a peer-to-peer network for trustless execution and recording of transactions. I like to use the word trustless, just as in software engineering, we quite often nowadays talk about serverless, or previously with web architectures about stateless. Stateless interactions in a web context doesn't mean there's no state. It just means it's not the server managing the state. And same for serverless computing. It doesn't mean we don't have servers. Yes, of course we have servers, but we don't manage these servers. Same for trustless. Trustless computing refers to trust is managed in a very fundamentally different way. There's no central authority, no middleman, nobody in a particular role that would say this is correct, this is good, and governs basically any transaction. But it's the network, the community in itself. Okay? And thirdly, the architecture view. So with both definitions of the business view and the technology view, you can see that at the center of blockchains is the notion of transaction and transaction processing. And transaction processing has been a topic in computer science, obviously also for decades, ever since computer science exists. But if you think of relational database systems, you may recall ACID transactions: atomic, consistent, isolated, and durable, the core principles of relational database systems when transacting. With NoSQL stores, as introduced like in the early 2000s, and every cloud data store is a NoSQL store essentially, we had BASE, an acronym that was chosen purposely diametrically opposite to ACID, describing it's basically available, soft state, and eventual consistent. Very weaker guarantees than ACID. So with continuing that play with acid and base, taking an acid and a base together, the result is salt and water. Ignore the water. I would like to say blockchains are actually salt. Both the transactions are salt in this meaning here, as well as the systems that would cater for these blockchains. They are salty. Okay? We'll get to this. So in a system overview, at the bottom of everything, then there is the peer-to-peer network. What's of interest to us are the transactions. So any value that's being transacted among different partners in the network. Transactions are the finer-grained units in this picture. So we're grouping these transactions, a set of transactions, into blocks, and the blocks are being chained and referred to each other. Thus, the name blockchain. Okay. As you can see, with the first generations, we also had payments, of course, currencies involved with this. Blockchain, again, is the technology behind Bitcoin, and Bitcoin is probably still the most prominent or successful example of an application of blockchain. With the second generation, then we had smart contracts, and smart contracts are executable programs on the blockchain. Now, given this as a starting point, trustless computing, business disintermediation, using a set of concepts from computer science, what can we do with that? Nowadays, we have a number of blockchain networks out there. We can also separate them between public and private, or public means permissionless, and private means permissioned. So these are completely open networks, Bitcoin, the Ethereum platform, and different systems emerging. I'm not going to say on a daily basis, but there's plenty of different blockchain networks out there. And on the other hand, we have the private networks, which tend to be favored by the large-scale corporations, which take in some aspects of blockchains, but probably not all of them. So a permissioned or private network requires a membership model, and only particular members can participate in the network. And then you may ask the question, who actually decides on the membership? And isn't there somebody who will decide on the membership? And the moment I have such an entity that decides on the membership, am I not introducing trust again? So, but this is something we can discuss probably later on. The main characteristics, if you look from a technical perspective between the public and the private network, can be related to questions like identity management, access management, the consensus protocol that is being used, the trust that is being required or not required, and of course the different applications that we have there. And the range, of course, is huge. Now, and I will not go through some of these details, but again, the starting question was, if we have a technology like blockchain, or we have different distributed systems technology platforms, how am I actually building an architecture that would fully utilize the platform's capabilities, exploit these to the best way possible, and does not violate also the properties imposed and introduced by the platform? So this is really the key question. How do blockchains, if at all, change the way we design software application architectures? So you may take the position, say that an application architecture should be ideally independent of the underlying platform model, independent of the underlying data store, independent of the underlying middleware system, the programming languages, the entire infrastructure being used. But we know this is not really the case. This is not true. Any application that will be built purely independent of an underlying infrastructure would probably not use the infrastructure efficiently. Okay? So I hope we have an understanding now of what blockchains are at least initially, and what they are about, and I hope you could all tell me now the difference between a blockchain and a cryptocurrency. A blockchain is really the technology behind the cryptocurrency, but it's a technology that can be used independent of cryptocurrencies. Okay? And the key aspects why we're interested in blockchain and why the platform and technology as such has been created and exists, some of the elements are listed down here. It's immutability of data. Once the data is stored in a blockchain, it cannot be changed. Just that first aspect, if you take that, that's why many banks are so highly excited about blockchains. Suppose you really had this golden record of data in a distributed data store that cannot be changed. You could rethink your entire auditing processes in your organization and probably get rid of most of these auditing processes. That's quite powerful. The decentralized control. There's no single person that can manipulate the data, not even a database administrator as in a conventional sense. Nobody does this because, in fact, the same copy of the data exists with every peer in the network. It's resistant to censorship. It addresses issues of data deduplication, proof of existence. The latter point in particular interesting for any supply chain scenario these days, and actually being able to track where an item originally came from without being able to manipulate that. So at TU Berlin, we started to get excited and interested in blockchains about 2-3 years ago. And we started initially with a set of smaller scale projects. And one of them was the idea to implement chess on the blockchain. The idea was not to revolutionize the entire gaming industry, but if you do think about the online gaming industry, yes, it does require typically a gaming provider. And the moment 2 or more players will play an online game, they trust that provider. They trust that provider that everything will be fair, that the provider will not manipulate the game and so forth, as opposed to playing directly with each other. Okay? And so a student team, together with members of my research team, and in joint work also with Ethereum as a foundation directly, which are based in Berlin also, we built a chess game on Ethereum. And later on, a few students blogged about this on the Medium platform, and shortly later, another blogger put this up, and within 2 days we had 25,000 reads of this article. It's an impact that we can't easily achieve, in fact, in academia, but goes quite fastly with what we did. So what's the idea? The idea is, wouldn't it be nice to have 2 players play chess on the blockchain? And again, doesn't it fit nicely? Every move that is being made can be recorded persistently in the history, will not be able to be changed, cannot be manipulated by anybody else. Okay? That's the first attempt. We will soon see that this is not the way we should build the architecture, because putting every move in a chess game onto the blockchain, on a blockchain, will simply not scale. And not only putting each move on a blockchain is not wise to do. Similarly, in the particular application case of chess, the question is, what about checking the endgame condition? And checking an endgame condition, in fact, can be quite costly. So the basic model really looks like this. So chess is a specialization of a turn-based game, and it's being modeled as a contract, as a smart contract. So this is the behavior that on every peer can execute, and a client would execute with the contract for chess, and the specific chess logic and authorization, other aspect can be put into libraries. Even though it's a simple example, we're not talking about a very large-scale system here, we already have quite some tough challenges encountered. First, the checkmate condition is just too complex to be checked on the chain. Right? And if you don't check it on the chain, so what would be alternative ways? And I will show you our solution in a few minutes, to do it differently while not violating the property, not introducing trust later on by doing it in a different way. Secondly, all computations cost money. So can we do it differently? Can we think of a platform that would be more cost efficient in the way we're actually using the blockchain? Blockchain is not a technology that should be seen as a silver bullet, and then you can put everything and do everything as you have always done onto the blockchain. But this is my main point, in fact, in this talk. Once we have a technology like this, how do we build an appropriate architecture? How do we think and conceive of an architecture that would be well suited to the technology? A second example is the old story of an online service marketplace. So this is the opposite of Apple's App Store. And said, the idea would be that each and everyone who is a service provider or a service consumer basically can exchange the use of the service and sell them directly without the middleman, without that central marketplace owner. So think of a marketplace that would be fully decentralized. Right? And this obviously is a much more complex undertaking than the chess game at first. The idea would be that a consumer like Alice would buy time-constrained access to a provider's service that is exposed, let's say, to web APIs. And a provider equally basically can charge for that use and makes money out of selling that. The illustrated architecture that we came up with in this project, and this is actually a project where the paper of which will be presented as we speak, today or I believe tomorrow at the EoSE conference in Spain, which is running in parallel this week. The idea really is that we need a bit more of logic, of contract logic, on how to achieve this. So again, allowing every service provider to sell the services directly to other consumers for a given time period. And as the figure already illustrates, again, we've been using the Ethereum platform for this purpose, but in combination with a dedicated file storage system. Service monitors for quality measurements have been still external, so to say, to the direct peers. The illustration and the main point for here is that with a second example, next to chess, we found even more challenges. One, for chess, we found that computation on the blockchain can be quite expensive or too expensive. With the service marketplace example, there's a particular indication that data storage itself on the blockchain can also be too costly. So if you think of service marketplaces and the traditional notion of marketplaces, you would have elements such as service discovery. Okay? But again, if we follow the true blockchain thinking, a copy of the entire registry of services would need to sit on every peer. And that's way too costly. Simply pointing from the blockchain to some cloud storage where the registry, the service discovery would take place, would again introduce trust into the cloud storage provider or some service discovery element which we don't want to introduce because we want to have a purely trustless system. That's the main idea. And the moment you start to introduce these individual trust elements again, you're breaking the entire property, right? So the question is not only for computation as in the chess game, in this case, how can we actually move the data off the chain? Second, at least this applies to all the public networks like Bitcoin and Ethereum and the like. Everything that is on the blockchain is publicly visible. So if Bob sends Alice money and vice versa, it would be publicly visible. That's the entire idea. Everything is fully transparent, and therefore everybody on the network can actually see what has been transacted. Now, in some cases, this may not make sense, or it may be difficult to implement. In this case, for example, of the service marketplace, if you sell access to a particular service, how would you put this on the chain without revealing everything too early? Simple encryption may easily break verifiability. So the whole point then is to introduce a model or to find ways that to operate on private data without revealing the elements that you want to keep secret. Okay. All right, so thinking again about the interrelationship and the interplay between blockchains and architecture, we've seen two examples, one rather simple example, one a bit more complex example, that even though we have a blockchain and a very powerful, very promising concept, still it's not a good idea to put everything onto the blockchain, but to have some elements off the blockchain. We're calling this off-chaining, so to move computation and data off-chain. And this, again, has an impact on the architecture. And we're doing this because even though blockchains already address so many properties, in public blockchains, you don't have privacy. There may be limits to scalability, and there may be limits to cost-effectiveness. Okay? And there may be other qualities, enterprise qualities, that arise. So off-chaining, and looking at the time, I'd like to talk a bit about off-chaining then, how to move computation and data off the blockchain without compromising the properties that are introduced with blockchains in the first place. And this is both a platform and an architecture problem. If the platform does not take care of this, then you need to take care of it in the architecture. But probably as we speak, people will think of new platforms, and some of these features or elements will actually be introduced and result in new features in the platform. Then, of course, you can relieve your application from that responsibility. So it's a cycle that continues, and we have lots of different things to observe in this context. What we have devised out of these 2 projects and a set of other blockchain projects running in Berlin is a set of 5 design patterns. We're calling these design patterns, well, we can discuss to what extent they're purely design patterns or to what extent they result in platform elements or in strategies that would really result in the platform architecture in itself. And you see they're also of different complexities. Some appear rather simple, and some are actually very complex. Let's think of a first pattern. I'll run through these patterns, and I won't be describing each of these patterns in detail. There's papers if you want to read up on these more, but I'd like to give you a picture on how we approach the general idea of moving computation and data off the chain. The first one is simply use challenge and response as a pattern via smart contracts. So use smart contracts to model a state machine. Actually executing a state transition is cheap. Computing a straight transition, however, is expensive. So why not just do that off-chain and then use a challenge response model? It's just like we do. So in the chess example, and I can show you this, and it may not be well readable, but you see some of these challenges listed up there. These challenges basically are you're claiming a win by checkmate, or you're offering a draw, or you're ending a game. This is a claim. You're putting the claim, so to say, and then the opponent can challenge you and say, well, actually, no, this is not checkmate because I found a way. And again, a very basic idea of taking the computation off the chain by introducing a simple challenge response pattern. Nevertheless, you need full state modeling, and then the actual state model in itself is what you would encode in the contract then. Okay. The second one is, and this is also primarily driven by the chess example, or nicely illustrated with the chess example, but then it applies also to many other blockchain scenarios, is don't put everything on the blockchain. Right? And you see, if we have 2 players here, player 1 and player 2, there's only a few things that actually need to go on the blockchain, like game initialization, joining a game, the claims that we just saw, and then the exception of sending a state if you want to write a global state onto the blockchain. But in fact, the individual moves of the chess game you wouldn't need to put on the blockchain. What you would need is a secure communication channel between player 1 and player 2. You can use Ethereum's Whisper, but you could use any other communication channel as well, if coupled with signatures. So the idea is that 2 parties that want to transact, they just transact outside of the blockchain. But what they do is they sign each other's messages, and they agree on it, and once they do their own state transition, so to say, and once they want to write back onto the blockchain, they can do so by including the signatures. And this is what we see also with related work, payment channels, and many other really interesting and nice and powerful concepts are being created there, so that you take the transactional interaction off the blockchain. Yeah. Very powerful concept in using signatures. Thirdly, if we have large data that we're storing on the blockchain, and obviously space is limited, the idea is to use an external storage service. But we can't just use any external database, neither relational database or NoSQL store. Again, we would introduce trust, or we would break trustlessness by introducing such elements. So there are systems out there now that deliberately target either the blockchain specific application development, or you take any storage that is content addressable. So if you have your actual data stored, your mass data probably externally in a database, you create the hashes and you put the hashes, the uniquely composed hashes, onto the blockchain. In this way, you ensure verifiability of each of the peers related to the actual data that is being referenced at. Okay, this is a fairly seemingly simple pattern, but of course there's plenty of consequences in doing so. Number 4 is what we call delegated computation. On the left, you see what the basic blockchain model is. Any transaction is being executed by every peer in the network, is being recorded in the ledger, in the copy of that every peer maintains. And this is, of course, the overhead, but only in doing so, we are getting the properties that we initially wanted. However, this can be quite costly. This obviously is very costly. And this is also one of the reasons why some blockchain networks don't scale very well. Why don't you think of moving the computation outside the blockchain to some external party like a prover? However, again, without introducing the trust. So the idea is to move the computation outside of the network, but to allow inside the network everyone to verify the proof. Let's say, for example, you are calculating prime numbers. There's no need that everybody would calculate these prime numbers and incur the costs. You have the prime number be calculated elsewhere. But then you need to allow everyone in the network to verify whether the prime number is actually a prime number. So moving something outside of the network is only, of course, in this case, usable and senseful if the verification costs less than the actual computation. Right? Now, the problem is that verifiable computations are extremely complex to specify, and they also require a deep technological understanding. This is where one of my PhD students is doing very excellent work, Jakob Eberhard. He has developed or is developing a system called Socrates. It's available open source. It was just presented last week by invitation also from the Ethereum Foundation at the DEF CON meeting. And the idea basically is that you have a higher level language in which you can program the code that you want to have executed off-chain. You map these to different mathematical concepts and have the prover, and then you map this back to the Ethereum blockchain. If you're interested to find out more about this, again, I'll invite you to follow the links and the papers that we have on this. And finally, for the load contract footprint pattern, this is the core idea here is that to learn from the experiences we're making in dealing with blockchains of how to use the system appropriately in the sense most effectively, not to overstress the system, in this case, for example, optimize for writes, not for reads. Basically, you have to, every transaction on the network charges a fee, costs money. So again, taking the cost factor into account, how can we minimize the cost and still do computations offsite? In the service marketplace example, for example, you want to check who is actually allowed in the network to access the service at a given point. There's no need basically to have this written as a transaction on the blockchain, but you can actually compute this locally from given data sets. Okay. All right, so much for an introduction into what blockchains are. I'd like to show you a few more applications or other applications. These are not my applications, but these are applications that I find particularly fascinating. One of these applications, for example, is a banking bridge that Citibank and Nasdaq introduced earlier this year during the Consensus conference in New York in May. And it basically allows straight-through payment processing between Citibank and Nasdaq. And this is blockchain-based, and it's live. Okay? So this is not a proof of concept. This project, in fact, started end of 2014, 2015. So probably many of you who are in the position now thinking of, is blockchain interesting for my corporation or not? Some of them were at this stage a few years ago. Why is this fascinating? The finance sector hasn't really seen any banking bridges so far. Every bank has its own IT system, and they're not linked. Right? So one of the core ideas in the blockchain world is that within a business network of interacting peers, everybody shares the same set of data, has the same copy of data, and has this in the network, there's a completely different trust. This is a model that we simply didn't have in the past. Or for those of us working in web computing, there was never such a thing as a global schema for anything we wanted to. Suddenly we can introduce this for business networks. Again, I have no relationship, was not involved at all in this project. But again, in looking at this, we have to be closer, to take a closer look and understanding what are the architectures. And that's quite difficult sometimes to do from the outside. But the interesting part is, how does the application architecture, so the actual payment processing, then look like in doing this with the blockchain, as opposed to having done this prior without? Another example, and supply chain is a major area in the blockchain space, in particular supply chain provenance. This is an example from a small startup company called Provenance, based in the UK. And they hit the news a couple of years ago with their tuna blockchain case study. So the Genesis record of the digital footprint for a caught tuna fish is basically being created when the fisherman in Indonesia would actually catch the fish. Okay? So, and from that moment on, the digital record and the movement of the fish through any redistributor, sellers, factories, whatever, until the fish would actually land in the shelf in your supermarket can be traced. That's at least the idea. And the idea is, of course, really nice, because such provenance, again, not immutable, cannot be manipulated. Nobody was telling you, right now, if you buy a fish, you don't have any proof of where the fish actually comes from. You may have to trust an authority telling you, well, this came this way, but it's purely your trust whether you believe it or not, right? Or you believe in a certified agency that says this was caught according to friendly rules related to fishing. This is all your trust in imposing that. If you basically take the original blockchain idea, basically now we suddenly have this. And you can see this has nothing to do with cryptocurrencies per se, but introduces very interesting models. The same applies to the used car market now, or to any parts management in IoT context. And this is why the earlier map of the startup landscape or the systems out there is so increasingly large. Nevertheless, same here, if we then take a closer look into the architecture of the system, we'll see, well, it's not purely that nice. First of all, there's still a discrepancy between the physical good, the tuna fish, and then the digital record. Yes, the digital record cannot be manipulated, but in fact, the physical good could be manipulated. Nevertheless, it's still a huge step forward as opposed to what we have currently, or what we had in the past. And why this is happening on the public blockchain, IBM is pushing with Hyperledger many of such supply chain scenarios. They're running large projects with Walmart in the US and have examples from strawberries and avocado shipment from Africa to the US. And again, with many of the such limitations, but again, it's a huge step forward as opposed to what the previous state was. And still some research left to do in improving the architectures. Also quite interesting, energy markets. And so we were just awarded a new grant from the German Ministry for Economics and Energy. And this project to write block PV supposed to start in Q1 next year. And the idea is to allow producers and consumers of photovoltaic energy systems to trade their energy directly. And this is both for reasons that the energy market in itself, the energy systems are changing significantly in being fully decentralized, and we're looking for alternative ways to trade energy. But it's also related that if there's ways to equip individual photovoltaic providers and consumers with corresponding energy batteries, that the battery management itself could also be blockchain-based. So this is something we're very excited to start with. And from the idea, it's very related, very similar to previous projects that have been around also in this world. So the Brooklyn microgrid probably was the first to start such a decentralized energy market, but initially it started with about a handful or 10 households. PowerLedger is a company in Australia that takes on the same idea for decentralized energy markets Again, does it differently than Brooklyn Grid, but in the spirit very related. But Power Ledger, again, has a different architecture or different details once you start to look into this. And for Block PV, we hope to be able to actually demonstrate something nice in Germany in a short time, hopefully. All right, so to summarize, the potential for blockchains to transform how organizations produce and capture value, I think is huge. And it's also very real. This is not just a vision, but it's happening, and there's many proof of concepts and beyond proof of context production systems already out there. If you look at how does the architecture influence the other, or how does platform and architecture are in interplay, it all relates to this notion of trustless computing, which I think needs further refinement. Obviously, it's something that I'm just throwing at you now, saying, well, what is trustless computing? But I gave you examples on what this actually means. You can't introduce a new component easily, or some element that, again, would break the properties introduced earlier. Similarly, so we have a number of enterprise qualities coming up. We started basically with a trustlessness property, but of course, any enterprise quality related from high availability, scalability, privacy, anything that's being introduced will change the way also the platforms may look like. So the entire cycle is frequent, if not continuous, and must be carefully observed. So whoever does research in and development in the blockchain world obviously needs to have this ongoing radar of what's going on in the world, and this is at very fast pace. And sometimes I feel reminded back to the cloud computing days, the early cloud computing days. We started to think about cloud computing probably around 2005 or so. And back in that time, it was a similar concept where people thought, will it really change the way that we build systems? Nowadays, it's a de facto standard for us to deploy our systems. And I'm of the opinion that the same will apply to blockchains. We're at a very early stage now, but it will become, of course, mainstream over time. With that, I'd like to conclude my talk. I'd like to thank you for your attention. I'd like credits to give to two of my blockchain leads, Jakob Eberhard and Markus Klemms in particular. And I don't know if we have time, but I'm happy to take probably one or two questions. Thank you.
Björn, please. Just wait a minute for the mics. Oops. Over there.
How will quantum computer influence blockchains?
I don't know. I'm not sure whether you're referring purely to computational power. Again, we need mechanisms, at least within a public blockchain network. Computational power alone will not buy you the possibility to break the system. With the private networks, we're looking at a different scenario. Of course, computational power is going to be critical, it's going to be very important, but I think on that abstraction level, it's going to be difficult to answer that question.
That was an easy question, perhaps a more complicated one. Erik, oh ja.
Thanks for the presentation. You mentioned the word cost efficient a lot of times, but we read now that Bitcoin transactions use as much power to actually mine than half of San Jose, like 300 households. Can you say more about this cost efficiency?
Well, okay, so cost efficiency is one target quality, and we have many of such target qualities. Again, we're starting with all the typical non-functional properties we've ever seen in enterprise computing: high availability, scalability, take any illities, reliability, and so forth. And we're adding now even the non-technical or the more business-driven criteria, such as cost effectiveness. Obviously, they have to be seen in balance, and they have to be seen in contrast to each other. But then the main point I was trying to make is that we can't or should not take an existing architecture or the way we have thought about transaction processing for the last decades and then just map them to blockchains. And you can see some of this discussion always ongoing. Quite often Visa transactions are being used as a benchmark, and they're saying, well, Visa runs roughly, I think, 60,000 transactions per second. And then somebody tells you, well, Bitcoin is at 7 transactions per second and Ethereum at 15 or so. But there's even other blockchain networks out there. There was just recently one published from University of Sydney, where they're actually even higher in scale. But then how would these numbers compare if you have single-digit or two-digit transactions per second compared to Visa transactions? Well, the main point is don't take the Visa transaction model and put it onto the blockchain. That wouldn't scale. But think of the blockchain-specific properties and put what you want to have on the blockchain, and the other basically do it differently. But then what you gain is significant, and you're not just mapping and migrating a system from A to B, but you're fully transforming the system to properties and possibilities that probably were not there before. And that's why it's so exciting.
Okay, Stefan, thank you very much.
Thank you.